All right, so how does this work? Well, now I'm on the slide on Huffman trees in the computer on our slides. We will use, as I mentioned before, a binary tree and a priority queue. Right, and the idea here is that Go Eagles requires 144 bits in Unicode, but only 38 bits if we use Huffman encoding. So that's kind of there. So here is, if we took the entirety, that frequency table for the English language and basically normalized everything, like for every Z we see, we would expect 86 characters. For every Q we see, we'd expect 103 E's. For every J we see, we'd expect 21 F's, right? If we see 21 F's, we'd expect to see 63 O's. If we normalize everything, well, kind of unnormalize everything, we'd get this table of frequencies. And we would use that to build an encoding that looked like this. We'd use it to build a tree that looks like this. So we would use 3 ones in a row to represent a space. We'd use 0 followed by a 1 followed by a 0 to represent an E. We'd use a 0 and 3 ones to represent an N. So only 4 bits to represent an N. And it would take, for a Q, it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits, I believe, to represent a Q. So how do we build this thing and how do we read it, right? How does this thing actually work? It's an excellent question. The idea here is that we are going to, what we're going to do, if we've got a document like, again, our Shakespeare document here. We've got our Shakespeare document. What we would do is that we would read in all the characters of this document, okay? We'd read every single character in this document, and we'd produce a count of that. Now, how do we store that? We learn that later, but the best way to do that is to use a hash map. But for right now, the idea behind counting everything and making a table like this isn't too hard to do by hand, which is how we're going to be producing these Huffman trees. We'd just simply be counting every character and how often it occurs. For each character, how often does it appear in a document, right? So, and then what we'll do is that we put these items into a priority queue, ordered by their weight. And the weight is the frequency at which this frequency counts. So the frequency occurs, like a space occurs 186 times. So the more often that symbol occurs, the more bits that can be saved by giving it a smaller encoding. The higher the weight, the more important it is, therefore the more frequent it is, therefore the more we'll save by giving it a shorter bit character combination. So what we'll do is that we will put the items in a priority queue, and the priority queue will be sorted by weight, with the smallest weight up front, the least important things up front. And then the algorithm as follows. We take the first two things off the heap, combine the nodes into a parent node, and then put that node back into the tree. Now that sounds a bit weird, but I will go ahead and just show you how it works. It's easier to show you it's easier to show and then explain what we're doing than to explain what we're doing and then kind of show you. So we'll go ahead and do that.